For tuning into my talk today, which is about linear programming bounds for quantum amplitude damping codes. I'm Yingkai Ouyang from the University of Sheffield in the UK, and this is work done with my co-author, Ching-Yi from National Jiao Tong University in Taiwan. So in this talk, I would first review linear programming bounds for both classical codes and quantum codes. Next, I'll talk about amplitude damping codes. And finally, I'll talk about linear programming bounds for amplitude damping codes and explain how we obtain these bounds through the introduction of a new technical tool known as auxiliary exact weight enumerators. A central problem in coding theory is given code parameters, which is the length of code n, the number of encoded bits k, and the minimum distance of the code d, what is the maximum k or d that we can have? We can obtain upper bounds on k or d using linear programming methods. Namely, we can write down a corresponding set of linear constraints for our NKD code. And if this set of linear constraints is infeasible, we can make the conclusion that no NKD code exists. So for small n, we can numerically study the infeasibility of these linear constraints. But when n is large, numerics will fail, but we can rely on algebraic bounds from Del Sarte's method. Now, given a classical code C and its dual code C perp, we can write down the weight distributions in terms of A's and B's. The MacWilliams identity connects the weight distributions of the A's and the B's through this set of linear inequalities over here. Here, AI and BI count the number of code words in C and C perp of Hamming weight I, respectively, and because these are binary codes, we use this binary Kvachuk polynomial over here. So, because of the code's promised distance d, we automatically know that AI equals A2 and all the way to AD minus 1, and all must be equals to 0. Moreover, we have the MacWilliams identity over here. So for this NKD code, we automatically have this set of linear constraints. And moreover, we know that all the A's and the B's must be non-negative integers. So we not only have a linear program, but we also have an integer program. And by determining the feasibility, if we can find that this linear program or integer program is infeasible, we can make the conclusion that no NKD code exists. A quantum code, unlike a classical code, is not a set of code words, but a subspace of an n-fold tensor product of a two-dimensional complex Euclidean space. Acting on this space are errors that can be expressed in the basis of Pauli errors. These Pauli errors are just n-fold products of the usual size 2 Pauli matrices. Shaw and Laflamme defined these quantum weight enumerators that can be expressed in terms of the code's projector P, and also the Pauli error basis over here. Remarkably, the quantum weight enumerators satisfy a quantum MacWilliams identity, which you can see over here, and is reminiscent of the usual MacWilliams identity for classical codes. So by writing down a corresponding linear program or integer program for certain quantum codes, we can obtain numerically upper bounds on the K and the D for quantum codes. And when the length of the code becomes large, we can use algebraic methods such as those for standard codes and also for entanglement-assisted quantum codes and quantum data syndrome codes. All these known results deal with Pauli errors, which bear similarities to classical quaternary errors. However, errors that are of interest that actually happen in specific physical systems are not arbitrary, but of a very specific type. For example, there's one type of error that describes the physical process of spontaneous decay from an excited energy level to a less excited energy level, and this is known as amplitude damping. The corresponding quantum channel can be written in this form with cross operators A0 and A1. The corresponding noise operator on an n-qubit quantum code would be an n-qubit quantum amplitude damping channel, given by the tensor product of this single qubit amplitude damping channel. Moreover, we can write down the cross operators in this form over here. And what's important is that we can count the number of times A1 appears in this tensor product to obtain the weight of the cross operator, which basically counts the number of losses that that cross operator induces in the physical system. And we can form a set of all cross operators that correspond to exactly I losses using this notation, Ki. And we can say that a quantum code corrects T errors perfectly if all the errors in Ki for I at most T satisfy the Néel-Laflamme quantum error correction criterion. We can, on the other hand, take a different perspective on quantum codes that correct amplitude damping errors. We can consider writing down weight enumerators for amplitude damping errors, where we simply take the Shor-Laflamme weight enumerators, and instead of using the Pauli error basis, we substitute the Pauli errors of weight I with the amplitude damping errors of weight I over here. And we can ask the question, what inequalities do these new amplitude damping weight enumerators satisfy? We can see from very standard techniques that we, just as in the case for the Shor-Laflamme weight enumerators, we have these identities, such as the fact that B's dominate the A's and which are non-negative. Moreover, the sum of the B's retains the interpretation of the fidelity of a quantum code without error correction, and hence the sum of all the B's must be at most 1. However, what is different from the Shor-Laflamme enumerators is that the value of A0 is different. For the Shor-Laflamme weight enumerators, A0 is equals to 1. However, from the spectral properties of our cross operators of the amplitude damping channels, we can find that A0 for the weight enumerator over here is at least 1 minus gamma to the n. Moreover, we also have an upper bound for BI by counting arguments, by counting the number of terms in this set Ki, and also by bounding the absolute value of each of these terms by standard matrix inequalities. So we can take a weight enumerator perspective on a quantum, on an approximate quantum error correction criterion. Namely, we can say that quantum code is a TC amplitude damping code if its weight enumerators satisfy the constraints BI minus AI is at most C times gamma to the T plus 1 for all I from 0 to T. And since gamma is a probability of loss in the system, it must be a number between 0 and 1. So with this definition of an approximate quantum error correction code for amplitude damping errors, we can revisit this amplitude damping code introduced over 20 years ago. So you have these logical operators, the logical 1 and the logical 0. And using the definition of the weight enumerators for amplitude damping errors that we have just introduced, we can calculate all these A's and the B's. And by taking the differences between the B's and the A's, we can see that this code, by definition, cannot be a 2C amplitude damping code for any positive C. Conversely, this code can actually correct a single amplitude damping error, which was shown when this code was introduced. However, what is lacking is a MacWilliams identity for our A and B type weight enumerators for amplitude damping errors. And let me explain this. So recall the definition of the A and the B type weight enumerators for amplitude damping errors. Namely, you replace the set of Pauli errors over here for the usual Shor-Laflamme quantum weight enumerators with the amplitude damping errors of weight I. And so you can collect all these numbers, all the A's, into a single vector over here in a Dirac bracket notation. and similarly for the B enumerators. And the fact that there's no quantum MacWilliams identity for AD errors means that there's no matrix that multiplies to A that is equals to B, or conversely. And because of this, we are motivated to introduce an auxiliary exact weight enumerator. So all of the information about the quantum code is contained in its projector. So the code projector can be written down without any loss of generality in a Pauli basis. And you can see these coefficients over here. Now, if we collect all of these coefficients into a vector, which we call phi, we can take the tensor product of phi with itself to obtain an auxiliary exact weight enumerator that corresponds to the code projector P. And it's quite obvious that this auxiliary weight enumerator is invariant under the swapping of the first and the second system because they are identical. And our main result is that while A and B, the A and B type enumerators are not directly connected by a quantum MacWilliams identity, they can be indirectly connected through these connection matrices. So, namely, the A type enumerator can be linearly related to the auxiliary weight enumerator, and the B type enumerator is related directly to the auxiliary weight enumerator by two different connection matrices. And because of this, we have an indirect relationship between the A's and the B's. Moreover, all of these relationships are linear, and hence we can write down a linear program for our corresponding quantum amplitude damping code to determine its existence. So if this linear program is infeasible, we can rule the corresponding TC quantum amplitude damping code to be one that cannot exist. And what's interesting about our linear program is that it has no integer constraints. And this is a nice feature because integer programs are hard to solve in general, which means that our linear program here is not so intractable to study. Moreover, this linear program concatenates. So what we mean by this is that if you write down this linear program for a specific value of gamma, and you cannot find that this set of constraints is infeasible, you are allowed to add many different values of gamma, which would make it increasingly likely that to find that the linear program becomes infeasible. And this is because while the A and B type enumerators do depend on the values of gamma, the auxiliary weight enumerator, which depends only on the code projector, does not. And hence, each of these linear equations over here, even for different values of gamma, while not directly related to each other, they're all related to the auxiliary weight enumerator, and hence they are all indirectly related. And by writing down a very big linear program, we can determine the feasibility of a small quantum code. For example, we have considered the case when we have a three-qubit quantum code encoding one logical qubit, so a logical 0 and a logical 1, and consider the correction of one amplitude damping error, and with this constant that is very large. And from our numerics, from choosing gamma to be 4 different values, we have found that the corresponding linear program is infeasible, and hence we have ruled out a huge family of amplitude damping codes that correct one amplitude damping error and is on 3 qubits. And from this, we can be quite certain that there aren't many good quantum amplitude damping codes on 3 qubits that correct one amplitude damping error. And this completes the presentation. So in summary, what we have done is we have introduced linear programming bounds for amplitude damping codes. We have introduced these these weight enumerators for amplitude damping errors, the A's and the B's, and also this very important auxiliary weight enumerator, from which we can indirectly relate all the A and B weight enumerators with the auxiliary weight enumerator. And moreover, we can concatenate these constraints to rule out, to form this type of very big linear program that can allow us to numerically determine the infeasibility of certain TC amplitude damping codes. And this ends the talk. Thank you for listening.